Okay. Welcome everybody to the Tree Fund webinar series. It is a pleasure to bring you our second webinar of the year with two speakers for the price of one. So we have two fantastic speakers joining us today on the webinar series. But before I have a chance to introduce them, and actually we have somebody that's going to be helping with our introductions today. But a few things I just wanted to point out as we get going. These Tree Fund webinars are possible because of our Crown and Platinum partners. These organizations that very generously donate funds to the Tree Fund to advance the research and the education that helps our organization are critical. We have their logos here posted. So thank you very much to those organizations that help support the mission of Tree Fund. A few housekeeping items. Introduction to myself. My name is Bo Broadbeck. I'm an extension specialist in community forestry and arboriculture at Auburn University, and also serving in the capacity as chair at Tree Fund this year. It's an honor to serve in that capacity. I would encourage people to consider funding and supporting Tree Fund. And I think there's a few key reasons why this is important. In 2018, we funded an assessment to look at the impacts of the research that Tree Fund is funded. As many of you know, Tree Fund is a philanthropic organization that supports research in the field of arboriculture and urban forestry. And more importantly, it supports applied research, research that trickles down into the best management practices and standards. And our assessment has found that many of the research that has been funded over the past 15 to 20 years is now being used in a lot of the standards of care that we use as practicing arborists around the globe. So there's a direct connection between the funds we provide Tree Fund, the research they do, and the iterative process of that research of getting down to the practitioner in the fields. So it's a fantastic organization with a good mission. And I think you're going to see that with a wonderful presentation that we have for you today. I know many of you are joining us today for continuing education credits. So we have a few policies with our CEUs. So, please pay attention. I know people are joining from various different ways, cell phones, iPads, computers, whatever it might be. We are pre-approved for Society of American Forester and ISA CEUs today. The way we handle our CEUs, as asked by ISA, is that through participation, and you're registering for this process, you provided us with your CEU and your certification number. Please note that ISA now asks us to please put it in the correct format. And I have an example here with the state or location in capitalized, a dash, the number, and then your specifics again in capital. So please pay attention when you do that. It keeps Heath, my co-moderator, a lot of time on the back end, putting it in the correct formats so that we can send these into ISA and keeps us from having any mistakes that might occur. Something else that's critical with our CEUs is that you must be on for the entirety of today's webinar. So it's critical that you're here from the beginning to the end. If the system kicks you on, re-sign in, that won't be a problem. We just ask that you're here for the majority of it. At the end of today's webinar, you will not see a CEU code. Instead, we will use this attendance records and we will send a report directly to ISA on your behalf, and they ask for 4 to 6 weeks to process that information. So, without further ado, I would like to introduce my co-moderator today. With me today is Jim Neeser, who is with the Davie Resource Group and works in their business development office, but is also here representing the Utility Arborist Association as their treasurer. It's going to help us connect the dots between the presentation we're going to hear today and some of the background of what funded this research. Jim, I will turn it over to you.
Thank you, Bo. As Bo mentioned, we're here today with part of the presentation on something that was funded by the UARF. So a little background on that: the Utility Arborist Association has always had a strong focus on research, but of course always struggled with the funding to pay for that research. And back in 2010, Mike Neal, who many of you may know, was working for APS and was one of the key people in trying to push forward to develop the UARF. And so at that time, we worked with the Tree Fund to develop that fund with a goal of getting to $1 million to make it fully funded so we could utilize that for research. Had very slow growth for the first few years, and the UAA put a push on to have it fully funded by 2017. I think that was put in maybe 2015 or so. And we did reach that goal in 2017. And the first grant was released in 2018. And I believe the first one was on cost effectiveness of IVM, which was also done by John Goodfellow, who's going to be presenting today. And we've had several other good topics over the years, cost of deferred maintenance, tree failure, IVM effects on plant communities, several great topics that we've had, including the one today that you're going to hear on characterizing the risk of electrical contact to arborists. So with that, it is my pleasure today to introduce the two speakers today. John Goodfellow is an expert consultant focusing on utilities, reliability, and vegetation management at Biocompliance Consulting. He has over 30 years experience in the electric and gas utility industry in a variety of positions, both in transmission and distribution and engineering. He's also been the principal researcher on several projects focusing on the modes and causes of tree-caused power interruptions. This work has led to development of a conceptual model useful in understanding and characterizing the risks of tree-initiated electrical faults on overhead distribution lines. He's also served on several standards committees, written pruning standards, a contributor with Dr. Alex Shigo. Long list of accomplishments for John Goodfellow. And joining John Goodfellow today, we also have Dr. John Ball. He's the tree care industry's leading safety expert. He's a professor of forestry at South Dakota State University, where he instructs courses in arboriculture, forestry, and emergency technician training. He also serves as the campus arborist. He's a board certified master arborist, a certified tree care safety professional, advanced EMT. And I'm sure I've missed several of their contributions, but I didn't want to take up the entire hour with all that these two have done for the industry. And so once again, to Bo's point, I would strongly suggest that you guys donate to the Tree Fund and specifically to the UARF, as it has a lot of great projects that get funded through it. So with that, I'll turn it back over and please welcome John Goodfellow and Dr. John Ball.
Thank you, Jim. And John, if you would share your screen to get the presentation queued up. While John is queuing up his screen, I wanted to mention real quick, we should have time at the end of this presentation for questions. Please put those questions in the Q&A box. It helps us as moderators have those in a single location, as the chat box can be extremely active. So once again, in the Q&A box. Thank you.
All right, let's get going here. So I really want to acknowledge and say thank you to Tree Fund. This was an important project. Dr. Ball and I proposed this topic 2 or 3 years in a row, and we kept tightening up our proposal, and we were effective in being awarded the project under the 2021 grant. And the word risk is important here, because those of you that are familiar with tree risk assessment will recognize the model. We're basically using that concept. It comes from ISO standards on risk. And it has you consider the likelihood of an adverse event and the consequences of an adverse event. So we're going to talk about these 5 things today. The first 2 really are trying to describe what is the likelihood that an arborist will be adversely exposed. How does it happen? How often does it happen? John's going to tell stories largely on those first 2 points, and I think you'll find it very, very interesting. I'll pick it up at point 3, where we start to get into a little more technical discussion of the electrical issues associated with adverse exposures and what the consequences of those exposures are to arborists. So that's following that risk model, and it's a very useful one. I would also say that the Tree Fund is making this report available. We've got a 40-image deck to go through today. The report itself is 49 pages long. It's richly cited. We really did I think, a pretty complete job finding citations relevant to these issues. And it's based on a 20-year history of actual incidents. and it's based on over 20 years of high voltage testing. So we're pretty confident we've got a solid work product, and we are anxious to share it with you. So with that, I'll turn it over to John Ball.
All right, thank you, John. And for those of you that used to remember the phrase "next slide, please,"
Yeah.
you're going to hear that at the beginning, because in order to make this work, we have one person in charge of the deck. That's the other John, so you'll hear me say that at the end. To begin with, I do want to point out that our data field is from the United States only. And if we look at the United States, about 17% of all our arboricultural operation fatal incidences are due to exposure to an electrical current. That varies around the world. When I looked earlier at some of the other countries, the UK, for example, and such, they have a lower number, and there may be a number of different reasons for that. So for our international audience viewing this, the 17% just applies to the United States in terms of the frequency of this. The other thing I do want to point out for everyone is that we took a rather broad view of who an arborist is. If you were being paid to work on trees, you're included in this study. In other words, if I'm working for a landscape company, but I'm out doing tree work, and you had the unfortunate incident, then you're included in here as well. So it's a rather broad view of it, but what we're going to be talking about today is contact with an overhead power line. So John, next. Start out with is we looked at the data from a number of sources. Bureau of Labor Statistics is one of them. If you go through our report, you'll find in our methodology all the sources we used. But when we went through this, we had to go through and read the narrative. And as much as we could, we tried to cross-reference these. In other words, you get the data from one source and then you confirm it with another source to kind of build this large data set here. And when we looked at all this, we found that one of the leading causes of fatal injuries from electrical exposure was indirect contact, usually by a handsaw, next slide, or more commonly, a pole saw. In fact, using a metal pole saw in a tree was an extremely common source of a fatal incident in the United States. Next. We did a few stick figures here to try to illustrate these as well and try to make the point across here. But when we take a look at a saw contacted conductor, that was about 21% of the fatal incidences here. In fact, if we just said you couldn't use metal pole saws in trees, that would cause a significant reduction in fatalities in the United States. But reaching up and touching, and quite often these occurred from going through the narrative, is that the climber, which was the most common occupation, the climber was unaware there was power lines running anywhere near the tree at the time they swung it and touched it. Next. We tried to include a couple of narratives. I'm using a generic name, Jamie, just to give a little personality to this, to the deceased, if you will. But when we take a look at this, is what we had was trimming trees using an extended pole chainsaw, contacted a 7.2 kV overhead power line, and was electrocuted. And I use these two as an example. This is a condensed version of the narratives that we ended up going through so we could place these various incidences into categories. Next. The second one, which depending on how you divide it, could be the first. So I don't want to quibble and say these two differ by a lot, but our number two one was the climber. Again, climbers were the most common. The climber ended up cutting a branch, and either while they were cutting the branch deflected into the conductor, or they cut the branch, and as the branch either fell away or they were holding the branch, they made contact with the energized conductor. Next slide.
think I went too. Sorry. There you go.
All right. This partially cut, deflected where it remained attached, that was about 14% of the incidences. Now, by the way, not every narrative made it extremely clear. In some cases, they just didn't know. Had the person finished cutting it before the contact was made, or had it been completely cut? And so as best we could, we tried to separate these two, but you could also look at them as a large pool, and that is contact by a branch, because in both cases, whether it was deflected or they were holding it, it was indirect contact, either through the pruning saw that was into the branch or through the branch itself. But by trying to look at these, it looks like approximately about 14% of all the incidences were the person was cutting the branch, and as they cut the branch came down and ended up touching the conductor. Next. Again, an example here. Jamie was pruning a branch, 19.9 kV over power line, was making a cut. The branch tip dipped into the conductor and was still holding the saw on the branch and was electrocuted. Next. The other one was about 13%. So you could take a look and combine these and say, well, John, 27% of these fatal incidences were actually holding a branch, either through the pole saw or holding the branch itself, versus just having the pole saw itself coming in and touching it. So as I say, you could call this one number one and the other one number two. The point is, you're looking at three of the most common ways that arborists are electrocuted. In this case, the detached branch falls away, making unintended contact as it falls. And again, this appears to be about 13% of all the incidences. Next, please. Now, the narratives didn't always give us a lot of detail on the branches. In other words, the diameter of the branch, the length of the branch, where the contact was made. And so we don't have a complete data set that tells us this. But obviously the branch length, the diameter of the branch, whether it's alive or dead, can certainly have a major influence. Because I'm certain some people that are watching this today have had this occurrence where they cut a branch, and as they were holding it, the branch came down and swept the conductor, and obviously they're still here today. The other John will be going over that a little bit later on as the hows and whys. But John, next slide. Again, an example here, the rather small diameter branches, we were able to find some with that, where it was just something fairly small, long, and that swept it. Sometimes those were the non-fatal. And next slide. And then we also had ones where we had larger diameter branches, 1.5, 2, 3, 4-inch diameter that they were holding. Now, obviously, the larger branches, they were holding them and the contact was fairly close, obviously trying to balance that weight as well. But if you think of length, alive and dead, and diameter, John's going to come back to that a little bit later on. Next. And again, example here, branch about 5 feet long, was over the conductors. And as they cut the branch, it made contact with the power lines, was still holding it, and Jamie was electrocuted. Next. Number 3, if you want to look at, was aerial lift operators, or I should refer to them more by aerial devices, because it wasn't always an aerial lift as we often think about it, a bucket truck in this country. Some of these were scissor lifts, some of these were insulated, some of them were not. In many cases, we do not know whether the aerial device was insulated or not, or if the insulation was any good. But interesting enough, an aerial device operator was the most common direct contact. While we did have some with climbers where they back touched, by far and away, the most common was the aerial lift, as I'm calling it here, operator. Next slide.
Whoops, there you go.
Yeah, thanks. These were about 8%. So you can see it did drop off quite a bit. And a number of them were on this single phase wires. And I don't mean by this illustration, I don't mean they were always this. But this was kind of interesting that we had a number where what happened is they were touching a neutral and the phase wire. And quite often the neutral actually got caught in the lip of the bucket. and they were holding the lip of the bucket, unaware that the line was there, and then typically through the back, the back or the neck ended up actually making contact with the phase wire. We did also have them where it was a phase wire and a secondary. And in some cases, they were splitting phase wires, but those were actually the minority. Next. This is fairly common. Jamie was using a portable lift to trim trees from a customer's property. The lift was raised too close to the power lines, had his back, one burn mark, and on his arm. And again, this time they identified it as a portable lift. Sometimes we didn't even have that information. But again, if it was direct contact, the most common was an aerial device operator. Next. Now, we also looked at non-fatal. One thing that I'd like to point out, and I was very pleased with this, by going through some of the data, we were able to take a look at the ratio, if you will, of fatal to non-fatal in terms of incidences. With this, it appears to be about 1 in 4. In other words, 1 fatality for about every 4 serious non-fatal. By serious, 1 that requires medical attention. By the way, that is a lot tighter ratio than we find otherwise, which is about 1 to 13. The point there being is electricity is unforgiving. That when you do have an incident, the more likely outcome, far more than other types of incidents, is a fatality, though again, non-fatal actually are more. This one, again, cutting the branch, and as it makes contact, all right, this would be a non-fatal. Now, non-fatal didn't mean always just the shock. Quite often, these resulted in falls or swings. So in other words, they made contact. Some, they said they felt a tingle, and they lost their balance and fell into the tree, injuring themselves enough that it did require at least a visit to the emergency department. Next, please. Another one, and again, number 2 on this was an aerial device contacting the conductor and a ground worker touching the lift. In this case, about 12% of the non-fatal. I might also mention these were a little bit higher along line clearance arborists, that it was fairly common source of fatality for them, that someone was on the ground. Of course, quite often for utilities, the boom is attached to the chipper box, and we did have them where someone was feeding brush into a chipper that was attached to the aerial device, which is as the chip box, just as the boom made contact with the wire. Quite often, those were during line clearance operations. We saw very few of the step potential incidents, but we did see quite a few of these touch potential for non-fatal. Next slide. And we did get these where the branch was deflected. In other words, the climbers are working their way up to the tree, grabbed a branch, held it, added enough weight to it that it swung down and ended up touching the wire. Interesting enough, when we asked people going into this, what was the most common incident, this was one that was often identified for a fatal incident. But we had relatively few fatal incidences just from a climber deflecting a branch as they were holding it. But it was fairly common for the non-fatal. Again, quite often tingling, they fell, either they lost their balance and fell out of the tree, they weren't wearing any fall protection, or they took a bad swing into the tree. All right, next slide. And again, just illustrating that, hit it again, John, that in this case, you actually have 2 pathways. All right, next, John.
Okay.
And then take it away.
Yeah, that's great. Thanks, John. And John used a couple phrases that I want to clarify. And also, those of you that are perhaps more experienced with the concepts of electricity, a couple of these images or slides are going to be pretty basic, but there's a method in my madness. So we're really now talking about, we've said, how do people become exposed, right? What's the likelihood of an adverse exposure? Now we're going to start to talk a little bit about the consequences. And so obviously we have a hazard. The hazard is the power line, and the power the energy on that power line has the ability to do serious harm. John used the phrases direct and indirect. Just to be really clear, direct is when your body touches the object that's intended to be energized, the conductor. Indirect is when anything else touches it. So if you directly touch the line with your saw, it's an indirect contact. And I sometimes find people are confused by that. A couple other things that I think are going to be really important for you to understand as we describe how these incidents develop is the concept of a fault and a pathway. So a fault is basically the unintended flow of current from a source to ground, and it flows along a pathway. And the pathway is really important to understanding how these scenarios play out, because what you're doing is you're completing the circuit when you have one of these incidents. And it's the pathway that really tells us how someone then gets hurt. Okay, voltage. Okay, so there's a couple things that we really need to understand. So we are really only talking about the primary power system. And if you see on this table, there are pairs of numbers. John said it. If you get between two energized wires, you see much higher voltage. But thankfully, most people don't find themselves in harm's way in that scenario. Almost always, the incident involves an energized primary to earth or ground. And there really are a couple classes. There's the 19.9, which is 35 kV. There's a 25 kV class. There's 15 kV class, which has and that's where we did most of our work, essentially, at the high voltage lab, looking at 7,000 to 8,000 kilovolts. There are also some 5 kV class overhead distribution circuits out in older parts of town, which have lower voltages on the phase to earth. The thing about voltage is it's measuring the difference in electrical potential to 2 points. So we talk about step potential and touch potential. It's not the likelihood. Potential doesn't mean the likelihood in that description or those labels. It's the voltage. So substitute voltage, and you have step voltage and touch voltage. And another key point is that voltage will vary along the fault pathway. It's highest at the conductor, and it drops as it moves through the pathway, and it drops in relationship to how conductive the pathway is. And in most tree-related incidents, the voltage drop occurs really close to the conductor. And so the voltage that the arborist is exposed to is less a concern. And you can think of, we often have used this pipeline metaphor of pressure is the surrogate for voltage. Current is volume. And the difference between, well, not the only difference, but a key thing to remember is unlike voltage, which drops the further you get, the current is constant through the entire pathway. I'm going to come back to that point at several points during this discussion, because that's really important for an arborist to understand. It's the entire pathway is constant. No matter where you measure it, it's the same. What we'll be talking about mostly are milliamps or 1,000th of an amp. And the pipeline metaphor is volume. The third and final concept that's really important is to understand the conductivity of the pathway, and in particular, elements like the branch or the tool or the lift. And so I will be using the term impedance, which is technically correct on an alternating current system. But most people think of resistance, which is a measure of conductivity on a DC system. But just know it talks about how conductive it is, and it's a function of the property of the material. And it's the series or the collective pieces or elements of the fault pathway, the impedance of each, the sum total of those are what limits your fault current. Another thing to talk, just usually it's not a factor on injury incidents, but on interruptions and outages, the impedance of the pathway can change over time as current flows. Happily, most of the time in these incidents, the duration of the current exposure is relatively short. Okay, so what do we know about branches? So I did several projects for the Electric Power Research Institute. They are actually publicly available now. But here is one where we're looking at the impedance and conductivity of branches. And you can see branch number one out on the right side is out on the tip of that, the measurement point, out on the tip. That's where the conductor contacts the branch. And we see that we're seeing only 10 milliamps and 320,000 ohms. And you just kind of look at these numbers generally and recognize we see changes in orders of magnitude in terms of the conductivity from hundreds of thousands of ohms to hundreds of ohms through the plant material. If you look at the currents, you will see a couple orders of magnitude difference there as well. And that's what you would be exposed to. You can see why then this fault pathway and the concept of it being considered in its entirety is so important. On the right side of this diagram is basically a circuit model for a tree. And you can see that the highest impedance elements are up close to the conductor because that's where the little twigs and branches and new growth is. And as you come down the stem, as you come down, you're talking about kilo ohms. Then you get down to ohms. And we've got our little red hat guy down here. And above him from ground up is a whole lot of impedance. And that's one of the reasons why when you see brown leaves in trees in association or in proximity to conductors, that we really don't have a significant public risk of touch potential or step potential at ground line. Looking at conifer this time in a little different presentation of the data, we've got volts and we've got current. And if you look, now we're talking about time, you can see that the current would change milliamps over time as this fault becomes more energetic. But here's the important part. These are unusual and unlikely events. These are contacts with large diameter branches close to the main stem. This down in here is where we are most exposed. These are the smaller branches, and you can see we're down in the 50 or less milliamps. And so that puts that in context. But the key point again is you have orders of magnitude changes based on the characteristics of the branch or plant material. Here's the data in a little different format. A couple things to look at this again, and just kind of pan over it and you'll get a couple pieces of information. I'm not going to read that all to you certainly, but you have an initial current flow and you have a steady state flow. So what happens is you have a contact and there's a concept called contact impedance, which is relatively high, which has to be overwhelmed, if you will, before the current starts to really flow. And these are a little longer. This is 6.5 feet, 10 feet, and 15 feet. And you can see, you don't have to remember the raw number, just remember the range. We are here on a 10-footer, and we've got small, but there's multiple contacts. They're all 1/4 inch or less. And the diameter at the butt end is less than 2 inches. Even after a long-term exposure, we're in this range. On initial exposure, we're in this range. When you go over here, you can see now we're at 6 feet. We've got much larger diameter contacts. And it may start out still with some current being limited, but we have 4 amps, 4,600 milliamps, or 640 milliamps, as opposed to these. And that's a function of length and diameter. So one of the things that you need to understand conceptually, you don't need to understand it in detail, is how fault impedance varies. And the reason this is important is it'll help you understand how and why the power system protects itself and not you under various scenarios. So we have the either really high impedance or really low impedance faults. These are very easy to detect. These aren't so easy to detect. We've all seen or heard cases where wires are down and hot and sparking. So you can see the impedance here is orders of magnitude higher. And then on the schematic I showed you of the guy standing on the ground in the full length of the fault pathway from up in the crown down is orders and orders of magnitude higher or less conductive. And just by the way, a human body is about 2,000 ohms, and you have a contact impedance range of 3 to 5 before this becomes a factor, before the current actually starts flowing through you, if you will. So I want to dispel a myth. There is no way scientifically supportable that a scenario says at a distribution voltage that, oh, gee, I didn't get close, it jumps to me. So the power system generally, almost, there's some exceptions with quote unquote tree wire and coated wire, almost, well, the majority of the overhead lines are bare conductor, and we rely on the dielectric strength of air. In other words, the insulating characteristics of air and space. And we as an industry rely on people observing and not violating minimum approach distances. If that happens, we're all happy. But if you look at the distribution voltages, I showed you, these would be phase to ground. The highest one was 19.9. Most of them are in that 7,000 or 8,000 volt range. The air gap spark across would be 1/10 of an inch. It's like immaterial to your understanding of risk. When you're standing there at the end of a pole tool or you've got a branch, you're not going to see a 1/10 of an inch. And you should never even think, well, if I clear it by 1/2 inch, it won't jump. It won't, but you can't judge that kind of distance. The image here, just interestingly, this is, I had the privilege of working with EPRI at the high voltage lab in Lenox, Mass, where we did intentionally cause air gap spark across the trees. We're operating at transmission voltages up to 765. So it does happen, it can happen, but not on a distribution line. And this testing, by the way, is the basis for the minimum vegetation clearance distances that are included in the standard on the grid. So I've said it a couple times, I'm going to say it again. It's the entire fault pathway that really determines how much current you're exposed to. So you make the initial contact either directly with your body or through something. And the impedance of these tools is an important consideration. Tools or branches. Then it's got to get through your body. We know that's 2,000 ohms, more or less, through or across. But here's the part that usually isn't considered. The Z really deals with this. This is the minimum approach distances. But without considering this, you don't have the entire picture. So John said this, and I was going to say it a different way, but it's the same thing. When I first came into this business, it was not uncommon to hear people talking about, oh yeah, I got bit. So at least some of the people on this webinar have been shocked at low levels. You can remember probably what you were doing up here, but remember this part too, because if you are routinely working from a bucket and you get a shock because a branch you held brushed the conductor, the characteristics of that fault pathway from you down to earth really was super important, because if you had that same scenario and you were on an aluminum ladder, or if your bucket wasn't insulated, you would see a very much different level of current exposure. So it isn't just the MAD, it just isn't what's between you and the conductor. You can't do anything about you, but always think about this. And we can eliminate or reduce risk by thinking about the remainder of the pathway. It's a really, really important point. Okay, so I'm going to talk a little bit about the consequences first, qualitatively. And believe me, you can tell I'm a numbers guy. I'm going to show you numbers in a moment. But it's a hierarchy, it's a progression. So the first thing that the most benign is you'd have sort of a tingling sensation, getting bit, startle reaction, getting bit harder, maybe is the way you'd think about it. But this can be strong enough to surprise you. You can lose your connection to the tree. It could be painful enough that not only surprise, but you react and withdraw quickly. The next level of current exposure is basically being thrown. That's what people describe it as, because you've got this really strong involuntary muscle movement, and you can't control it, right? Up the scale now with a little more current. We've got this grasp where you got a contraction and you can't let go. You are frozen and you are completing the circuit. And this contraction can be violent enough to break bones. So just imagine breaking your own bones because your muscles lock up. Pulling the current up a little bit more, you have the possibility of an adverse cardiac event. And this is the majority of electrocutions occur because of this. And in fact, in our report, it says 99%. That's what the literature tells us. We're going to explore that a little bit more, but that's terminal conditions, shall we say. And then as the current goes up, we have increasing levels of burning, deep tissue burning, and we can also have burns due to radiant heat from an external source. So let's look at the numbers now. So this is one of the many of the important, let's say most important, not, but this is a really important part of our report. We synthesized this table based on a number of sources and had it reviewed by experts in the field. And so you can see what is the level of fault current that's causing these adverse reactions. So it talked about a physical reaction. So, you feel it, you got stimulation, you got muscle contraction, etc. You can't let go. Then what happens next? Well, you can also have tissue burning because the current's flowing through your body. And if you initiate the fault, but the current is actually not flowing through you, and you have a low impedance high current event with an arc in air, that's a 3,000 degree arc, hotter than the sun, and you can have really serious arc flash injuries as well. So here's the question I've always wondered about. I showed you that escalation. Let's go back just for a second if I can. No, that way. If you're dead, why do we care? But we see many. I mean, John said it, 4 to 1. People are hurt, but they're not dead. And they're seeing currents over this level. So how can that be? Well, it turns out, and Mark Kroll was a cooperator helper on this project. He explained it to us, and it makes all sorts of sense. So your heart is controlled by electrical activity. The T wave in particular is relevant to this explanation. So as it peaks, about half the cells are relaxing and the other half are still contracting. And you disrupt it with that impulse, electrical shock, and you can end up with unpredictable paths through the heart. Some cells are contracting, some are relaxing, and that's fibrillation. And you will be dead unless you are restarted with the paddles. You have to be shocked out of it or you're a goner. So it's bad luck to have the shock occur at the critical point in the T wave. But a lot of these electrical injuries are survivable, but profoundly life-altering. So it gets even more complicated, and we're not going to get into the full complications, but basically, here we are, milliseconds, so there's 1 second. Here we are in the range we've been talking about, 50 to 200 milliamps, and you can see where these incidents are occurring. The point I want to make is, until I introduce this concept, the time exposure is also a factor. So I mentioned overcurrent protection. I showed you high and low impedance faults. Here's the reality. Substation breakers are set at, they can handle up to 600 amps. Line reclosers are going to see steady state normal loads between 1 and 300 amps. Fuses, 5 to 100 amps. All of the injuries, almost all of the things I've talked about so far are under the current level of a 5 amp fuse. So it won't save you. The overcurrent protection system is to protect the system, not use. And in fact, almost always, the protective device did not open and interrupt the fault during one of these incidents. A couple of lessons from this all then is minimum approach distances are really important. Keep the tools other than insulating tools outside of it. I mean, that's what it says, right? But let's make sure we are really doing that. And any other conductive objects. John mentioned this. These extended reach powered chainsaws are a problem. I think it says in our report, all but one of the incidents involving a pole saw were related to these power saws, and they're hard to use, and there's a lot of injuries associated with it. Plant materials, we already established that they're conductive, and they can be attached to the tree, and so some of the current will flow through that attachment, or they can be detached and you can be holding it and all of the current will flow through you. It's difficult to judge distances at the outer length of the branch. We know the bigger and larger branches are harder to control. I know some of the line clearance contractors have a rule for their crews that if a branch is in contact, they piece it down, even if it's a small branch. And recognize that not only branches, but palm fronds and vines can be a problem, and we can be conductive, excuse me. And so basically, if we were to make sure that branches aren't striking the conductor on the way down, we could see fewer incidences. I mentioned this one, and I think we're getting nearly to the end here. The Z does actually not address the rest of the fault pathway. It's really focused on between you and the conductor. And we know that in the case of a bucket operator, or a climber, excuse me, it does give some guidance on positioning the climber relative to the tree and the conductor. It's probably a good idea that we think about a similar kind of item in reference to our aerial devices. And so here's a summary, and we have time for Q&A after this, but basically accidents are not random. Accidents are random and bad luck. But what we looked at, this 20-year history of incidents, electrical contact incidents, both injuries and fatalities. By the way, just so you know, electrocution is fatal, and electrical injury is not. So a lot of times the word electrocution is thrown around incorrectly. But we think this report is going to establish a basis for better understanding, and we hope that it's used to craft effective means of reducing the risk of arborists being hurt. So that is the end of the slide deck, and I think we're ready for questions.
Thank you, John and John, for fantastic presentation. I think you're absolutely right. I mean, tons of material here to digest, and we do have a number of questions. But before we jump in, just a reminder, I've gotten a bunch of comments. This is being recorded. It will be available on the Tree Fund website. Give us about 3 or 4 days so those questions about, can I rewatch this? Because there is a lot to digest here. Yes, you can. What's today? Tuesday. Maybe by Friday, we should have it uploaded on the webpage, as well as the final report, for those that want to dig deeper. So thank you to Dr. John Ball and John Goodfellow for putting together this research and sharing that material. So we do have some questions, and I'll jump in with the first one. And I think you did cover this, but it might be good review. Somebody asked, in the cases of branches hitting the line, is the size of the branch that is held or the distance to the line have any effect?
Yeah, absolutely. And it all comes down to the characteristics. So larger diameter conductors and branches can carry more current than small. The length of the pathway, the resistive elements are additive. So the more chunks you add into it, the higher the impedance. So longer pathways and smaller diameters limit the fault current much more than a larger diameter and a shorter diameter branch. And John also mentioned there's a really big difference between live and dead branches. But yeah, it makes a big difference.
And then, John, the only other thing I do want to add to that is that unusual one we found, and that was palm fronds.
Right.
Which seems to kind of go against what we've talked about already. But for those that are in palm country, holding a palm frond and having it touching a wire is definitely a fatal event.
Well, it might not be fatal, but it's definitely, here's the deal. They are more conductive. I actually have done high voltage testing with palm fronds now. And I think it has to do with the physiological characteristics. They're monocots, right? And they have this long fibrous transport system. So those fibers are great conductors. So for an equal diameter branch, the deciduous or woody branch versus a palm frond, the frond will almost always be more conductive.
And the point of that is that we often think of palms as the mechanical asphyxiation, that you're caught in the skirt,
right?
And you think that's the fatal event, and it is, but far more are electrocuted by holding a palm frond. And as John points out, now we're talking about materials in which it's made, but I don't want people to leave thinking that, palm fronds, because they're small diameter, that would not be conductive when they clearly are.
There's another aspect to palm too, and I know we said we're going to be brief with the responses, but the palms are so strongly apical dominance, and the fronds are the length they are, that the person up the palm doing the cut is almost always closer to the conductor than they would be if they were in a spreading canopy of a deciduous tree.
Next quick question for you guys. Do you know what percentage of fatalities are from line clearance workers versus non-line clearance workers in your research?
Yes, and we got that into our report in more detail, but let me point out, if someone is deathly afraid of being electrocuted, which I'm sure we all were or are, do line clearance. They actually had the lowest number. The most common, and someone asked this question too, was actually the small operator company. And again, we couldn't always get company size, but either a owner operator, one person maybe hiring a few people, or a small company less than 10 people doing tree work and landscape work at the same time. They had the majority of the fatalities. The larger companies, probably due to training, had less. Utilities, because they do a lot of training, and that's the only reason they're in the tree. The only one that stood out there was the unfortunate one where a ground worker was touching a truck.
Thank you. I'll take the next question here. And somebody wrote, I've seen climbers who have been in the industry their whole lives and they have no fear of contacting secondary wires or house drops. Is there any risk there?
John, I'm going to start with that. You finish it because you did discuss it. Mm-hmm. And I do want to point out that why it's not a high number, we do have every year where someone contacts a secondary. And in fact, they throw a rope over a secondary to kind of pull something off it. A branch is hung up and they just give it a flip, or even a throw line. And those are the incidences where we do see VFib.
Right.
And so, John, repeat what you'd done earlier on that, or talked earlier on that.
Well, essentially, I mean, you're right. It's the misfortune or bad luck of the shock occurring at the peak of the T wave.
Right.
There's another scenario, which is I guess gruesome, but if there is a short circuit between two phases on a service drop, which would be 240 volts, or sort of, you can have 480 on some of these services, by the way, secondaries. You may have this grasp and can't let go reaction, and you would be exposed long duration, and that could be really bad as well.
Right. So yes, there is a risk to answer that question.
We do know this though. So I don't think I'm letting the cat out of the bag. The latest version, the proposed version of Z133 Section 4 acknowledges that you can be trained to work around voltages less than 750, which would be the secondary class voltages. It's sort of like the incidental line clearance arborist that was added in the 2017 version. So, but even there, it's like, you don't touch it. It's like less than 2 foot, but you'll see it when it's published.
And it is, do not touch directly or indirectly.
That's right. That's right.
Couple of questions related to the weather. There's a few in here asking about the difference between wet wood versus dry wood, or live versus dead. And then also humidity. Does that affect the, spark jumping and things like that? So
yeah, those are important questions. And so the dielectric strength of air is affected by humidity, but not enough on a distribution voltage to make any difference. If it goes from 1/10 to 2/10 of an inch, doesn't matter. Water is important. It has 2 different aspects. So I mentioned this idea of contact impedance. So that's the impedance between, say, your hand and the branch. You have calluses, you got bark that's exfoliating. And so initially the current has to get across that contact. If the branch is wet, the contact impedance is much lower. So external moisture can be a consideration, certainly. The other question really I often get is, well, what about the seasonal nature, particularly in the northern hemisphere, I guess southern as well, anywhere you have deciduous trees that have a growing season where they're dormant and then they produce an early flush. Sugar maple is the example that everybody wants to talk about. Is internal moisture a factor? And there is some seasonal variation in impedance, but it's not really enough to move the dial in regards to the risk to an arborist. So seasonal pruning, if there's sap flowing or not, probably not an issue. Wet bark will make the fall. If the fall's going to happen, it'll happen faster.
There was a couple questions about, insulation materials available for arborist boots, and what should be considered here.
Okay, I'll start with that one.
Yeah.
And it's a flat out no. And here's my reasoning for that answer. Is when OSHA was asked, well, if we work with boots and gloves, may we do X? And OSHA comes back, no. You are not working for the utility as line personnel on that. You are allowed to work around lines, not manipulate lines. And so trying to utilize the PPE that what we used to call line people do, does not allow us to do any more. And we shouldn't take that as our safety measure.
Yeah, I agree. Personal protective equipment. So I ran line operations for a long time, and the rubber goods that are used are stored carefully. They're inspected. They're tested. You just don't want to go there, I think, with the tree industry. But I also say this, that it's the impedance of the entire pathway. So if you're barefoot versus having heavy boots on, there is a difference. There is a benefit. If you are wearing gloves, I'm not advocating rubber gloves, but if you are wearing gloves, the impedance across the glove is also in the fall pathway and will reduce the current you're exposed to. So there are reasons why appropriate clothing and footwear make sense and do, in fact, reduce the level of current you might be exposed to, but absolutely do not rely on that as a protective strategy.
And then last thing, I do want to jump in on that one too. I do want to remind everyone that burns are a very common outcome of contact with lines, and cotton is your friend.
Yes.
Wearing a lot of this synthetic clothing, remember, one thing we deal with is having to clean that out of the skin. So we don't have a clothing requirement, but watch what you wear.
Well said. I agree with that.
Oh, any more questions, Bo, or are we out of time?
Oh, I think we're at 1 o'clock, so I think we'll go ahead and bring this to a conclusion. I see that people are starting to jump off, but I want to thank both of you all for a wonderful presentation and a review of this research recently funded by Tree Fund. Thank you very much. For all of those of y'all watching out there, just remember this is recorded. It is available on the Tree Fund site in a few days. The full report's available and some other documentation. So if you have a lot of those questions, and I saw some questions, and we can go back and rewatch that material. For the ISA, CEUs, and SAF, just a reminder that we are submitting those CEUs on your behalf directly to ISA. And during the registration process, you gave us that certification number. So we should have that. If you have any questions about it, send an email to Heath Hoopke at treefundwebinars@gmail.com, and he can help resolve any of those issues. If you send them to me, I will forward them on to Heath. So with that, thank you everybody. Thank you, Jim, for helping me co-moderate this session and introduce this this series and this special project that Tree Fund has funded. So thank you. And with that, I'll go ahead and bring us to a conclusion. Thanks all out there. And just remember to support Tree Fund and keep them in mind. They do play an important part within our industry, not only keeping us safe, but making sure that we are better able to manage those trees out there. So thank you all and have a good rest of your Tuesday. Thanks.